Welcome to Magnify Your Message. Inspiration magnified.
I realized in the early 90s that we do science slowly. The whole process of science that humans are engaged in is slow compared to what it could be.
Welcome to Magnify Your Message. Are you concerned about AI and the negative ramifications of what AI could do? Well, you're not alone if so. But today, we take a look at some of the positives that AI can produce. Because today I'm joined by Dr. Justin Lancaster, a PhD scientist and researcher who's been at the forefront of climate change research everywhere from MIT and Harvard to Scripps Oceanography and the California Space Institute. Heck, Dr. Lancaster even appeared on the cover of the LA Times and the Boston Globe. He's done so much for so many. And today, on Magnify Your Message, Dr. Lancaster shares how he's developing groundbreaking ways to accelerate biomedical research using AI. In this episode, Dr. Lancaster is pulling back the curtain on fast science, a game changing approach to turbocharging research and tackling the world's biggest challenges, from climate change to curing supposedly incurable diseases. We'll talk about how AI could be used to help humankind and why the speed of discovery could be the key to saving our planet. So, if you're ready to rethink what's possible, you're in the right place. Let's dive in. Prepare to be amazed by today's guest. This is Dr. Justin Lancaster. Welcome.
Hi, Cheryl. Thank you for having me on.
Who are you? What do you provide? And who do you serve?
Okay. Uh, I'm a PhD scientist in oceanography, marine chemistry, as well as an environmental lawyer. And for many years in the last century, I worked on the climate change problem, carbon dioxide in the atmosphere, and on policy related to that. So I founded a nonprofit corporation called the Environmental Science and Policy Institute. And one of the key people helping me start that was a man named Roger Revelle, who was considered by many the statesman of science, certainly environmental science, in the 20th century. He pushed my career forward in the policy side and sent me to international conferences to present on carbon dioxide and the problems of humans facing environmental change that could come more quickly than we are able to adapt. And that all of that effort grew into a postdoc appointment at Harvard, connected to the Environmental Systems Center and the Harvard School for Public Health. And there I was looking at the human dimensions of global environmental change. So, short words, what's the impact of climate on people? And particularly understanding that 40% of the human population lives in coastal counties or in coastal states, and the vulnerability for humans to climate change is greatest at the coastline, where the sea meets the land, because that's where the weather of the ocean and the atmosphere have the greatest impact on humans. And the populations are very, very dense, much higher population density there. And a good part of the world is extremely vulnerable to environmental change. We in the United States don't completely understand that because we have enough wealth to protect ourselves from most environmental stresses. But in many parts of the world, that's not the case. Bangladesh and many of the island nations in the Pacific are very vulnerable. So we've known this since the 1980s, that we We're predicting a global climate warming of 3 to 5 degrees Celsius, average annual temperature increase. And of course, we don't really feel that as humans. It's going to increase slowly over a long period of time, but we do feel it in extreme events. We feel it because the average is made up of many spikes throughout the year or throughout the decade of extreme events, extreme cold, extreme warm, floods, winds, droughts, wildfires, some ocean issues that have to do with loss of coral and fisheries issues and stuff like this. So there are many issues where human society is really concerned, should be concerned about changing climate too quickly, and whether or not we're going to be able to adapt easily or with tremendous difficulty.
How on earth did you get involved in this in the first place?
Oh, wow. Uh, I had been a ski racer in Vermont as a kid. That's all I cared about doing. And so I went to school in the summer so I could train in the winters and ski. And at 16, I was done with high school and I wanted to go to a ski racing academy. I had a math teacher who said, no way, no way are you not going to college. And for some reason, well, we had a one-on-one relationship for 2 years, tutorials in this small high school I went to. And I knew she wanted me to continue in mathematics. And I knew she was right, that it would be very difficult to do that if I didn't continue. It's hard to drop math and then pick it up later. So, and for some reason, she had much more influence on me than my parents. Yeah, that's the way life goes, right? You find a wonderful teacher and
Right.
you let them influence you. So she figured out how to get me into Case Western University last minute, August. I was 16 years old, and suddenly my dad was dropping me off in Cleveland. And I'd grown up in this pristine little valley, hundreds of acres of woods in central Vermont, no experience with the city. And Cleveland was deeply polluted. The Cuyahoga River had just caught fire months before. Lake Erie was dying. The fish were all dying in Lake Erie because it was anoxic. The pollution was just intense in the 1960s. But the Clean Water Act had just passed. It had just come on. And so I got involved with some groups at Case Western that were involved with environmental protection of Lake Erie. And through that group, they took me down to a wonderful professor named Nairn, Ian Nairn. So I studied plate tectonics with Nairn, and he had a course where the second half was the carbon dioxide problem, which I didn't know much about. But after his course, I did. And I realized, oh, that's a very interesting problem, but didn't really grab me at that moment. What happened at Case Western was I had another course in comparative politics. And in the process of that course, I wrote a paper. And what I realized in writing this paper was that there's an inexorable development of human governments along a trajectory. It's an evolution of governments, much in the way that animals have evolved. Our systems of governance have evolved. And part of the course was showing us sort of where many countries in the world are behind us in the United States in our development. And of course, you can go different directions. You can go to communism, or you can go to parliamentary government, or to a republic like we have. And in this process, I also was developing the biological analogy for the evolution of government. And so there I was, very young. I was 16. I wrote this paper on the strong analogy between biology and the human society, right? That satellites are our eyes, white blood cells are the police. There's almost a direct analogy between many systems in our body and the systems that we have in a country or a nation to run our society. And that's what grabbed me. It was that idea that was so fascinating to me. And it was that that led me to want to apply to Scripps Oceanography, because they were doing origin of life research. So it was that. It was this push to Case Western to follow mathematics, which led into Nairn's introduction to CO2, getting to Scripps Oceanography to study origin of life and this analogy between biology and human society. And when I arrived, they rejected my, well, first they rejected my application. They said, we don't do that kind of research. That's philosophy. That's not science. And so I rode my bicycle to Scripps with the rejection letter in my panniers, up over the passes from Denver to Vail and down the other side, Grand Canyon to San Diego, and showed up and said, I want to come here to study. And I met a wonderful guy, Walter Monk, who was best friends with Roger Revelle. Walter Monk was maybe the most famous geophysicist in the world. And he's the one with Gordon MacDonald who figured out that the Earth wobbles on its axis. Lots of great science. And his best friend was Roger Revelle. He said, I want you to go talk to Roger, because I think Roger will appreciate that you're already a lawyer interested in environmental policy, but you want to do better on the science. There's some science you really want to learn. And I went to Roger and I told him all this stuff. And he said, that's philosophy. He said, instead, why don't you go down to my friend Charles David Keeling's lab, where they're measuring carbon dioxide, and see if he might have a use for you. So I went and met Dave Keeling, who was, again, very skeptical. He said, that other stuff is philosophy. If you want to do science with me, I'll let you wash some glassware. I washed glassware for the first half year, and then I started to take samples with his team, and I kind of worked my way into Keeling's group. And then I was there for 10 years. I had to give up studying the biological analogy between biology and human society. But I didn't, actually, because Roger founded UCSD. Revelle College is named after him. So he was able to just say, put this guy on special status, let him take whatever courses he wants. And it was fabulous. So I had cousins in La Jolla who put me up, which was also fabulous. I was a babysitter for their two young kids after, so I'd study. It was just perfect situation. And that led ultimately to understanding how important mathematical modeling of the dynamics of the real world is for science. Almost all of the environmental science we do couples to now modeling of that system. And what we were doing at Scripps was really the best work in the world, combining supercomputing, which had just come into UCSD in the 70s. It was just growing, but we had one of the first supercomputer centers in the country. And that allowed us to combine all of the data for the world and combine the chemical measurements with the meteorological measurements, the global modeling of the atmosphere and the dynamics of the oceans, so that we could get a prediction. When you're modeling a very complex system with many, many different stressors and many aspects of the human dimension, but many aspects of the environmental science, and all of your measurements of all of those fields of information have some uncertainty to them. There's uncertainty in the population or sample that you measure from. It's always going to not completely represent the entire sample. And you have uncertainty in your instruments, and you have uncertainty all throughout the process of science. And coupling and compounding those uncertainties is another science in and of itself. And so that was a fascinating period. And in that process, I realized in the early 90s that we do science slowly. The whole process of science that humans are engaged in is slow compared to what it could be. And I realized in 1994, 95, I wrote a paper that had to do with the aspect of mental modeling that the manager of a science project has to have when they initiate the project. And then this other modeling, data modeling of the dynamic system that has to go on in the scientific analysis after you gather data. The problem is that these mental models are rarely the same as the model that the experimental or field scientists have in their heads. So as I was realizing this, I came up with this idea of integrating the modeling with the environmental modeling or with your biomedical experimentation and your science management. And we did a project in the late 90s. We cleaned up the Charles River in 5 or 6 years. This is a Class D river. If you fell in the Charles River anywhere in the bottom 10 miles before the ocean at Boston Harbor, you went to the hospital. They took you and gave you shots. That was 1994. By 1996, I had a team of 80 volunteers who I used my method. I put together a whole data approach. I created a team of 7 university research teams, aggregated team, MIT doing the flow modeling, Amherst doing the fisheries, Bentley College doing metals. It was just really fun to bring all of these Boston universities together. And with the citizens, we monitored the river for months, but it essentially took us about 2.5 months to find every pollution source on the entire river, because the modeling in control allowed us very quickly to use the experimental resources to jump to various tributaries. When a rainfall event came through, I could make 3 phone calls, and I had 30 samples taken on the full length of the river by the citizens at 6 the next morning. So this was integrated monitoring, modeling, and management, which I called IM3. And when that, so I left that project with the Charles River Watershed Association, a nonprofit. They loved the citizens all engaged in all of these universities cleaning up the river. And in 2011, I think they won the International River Prize for the fastest cleanup of an urban river. It's swimmable now. So it's quite fascinating.
That's remarkable.
So that's one of my satisfactions in life, was participating in that and bringing that project to the Watershed Association.
So what are you doing now to accelerate the speed at which scientific research progresses?
I met a guy in Canada who came out of the Hinton Lab at the University of Toronto, a guy named Evan Stieg, who then with Hinton did his PhD in bioinformatics and started his own startup in 1998 called Molecular Mining Corporation. So the last 17 years, I've been focused on taking a part of what Evan put into his technology in molecular mining, which was convolutional neural nets. So neural networks, which are the basis of deep learning and large language models. So using neural networks to unravel very complex associations in biomedicine. And it's fascinating science. And now it's really taken off in the last 6 or 7 years. Evan's done a wonderful job of creating a bioinformatics tool that would be in the hands of a scientist. But can I make a computer automate the whole thing all the way through the experimental process in a laboratory? And I figured out, fortunately, I reached way back to the Harvard School of Public Health days and the human dimensions of global environmental change. And there's a whole mathematics that allows you to evaluate the value of information to resolve a problem. And it turns out that was the key to allow me to accelerate the entire process by letting the computer find the next best hypothesis in this uncertainty. to test. So it's involving uncertainty, it's involving hypotheses, it's involving machine learning, it involves the semantic web and graph-based causal graphs and Bayesian reverse engineering. So there's a lot of technical pieces that all get brought together to allow a scientist to do their science almost 20 times faster. And so this is, I'm somewhat gratified that I'm seeing this happening now in pharma and biotech. What I set as a direction in 2003 is actually happening. I've had 4 US patents issued for my version of this technology, the last in just 2022. And now I'm bootstrapping an AI system to bring this technology forward. And I call it fast science. And it will speed up science in biomedicine, and it will speed up science and engineering in climate change response.
And does it allow people to collaborate with one another, or is the
Yeah, very much.
okay?
Yeah, so it's essentially a database connected to an AI system on the back end, and the front end for the user is an adaptive learning gateway where elementary school, high school students, college students can go right in. And then the key piece is the automated lookup of a laboratory somewhere in the world out of the 4,000 contract research organizations that serve pharma and biotech. If you're on the biomedical side, essentially a reverse search. You might think Amazon for services. If someone's really interested and wants to see this in biomedicine, I have a competitor who I hope will become a partner called scientist.com. And they're doing a very good job of building an e-marketplace for biomedical research services. So I'm playing toward that because my technology and my patents reach to this instantaneous automatic push to an experiment to test that hypothesis as fast as possible. Tonight in Tokyo, or tomorrow in Seattle, or get the data back, automatically process the data. And here's the key. It goes back into a publicly accessible repository. Think of it a little bit like Wikipedia on steroids, because you would go into a space that you could collaborate with 10 other people on a very sharply defined question and do your research together. And you're kind of moving through the knowledge assembly or the knowledge graph a little bit like Wikipedia, but in your space is this entire experimental or field research capability at your fingertips. So, and you're being led to what you need to research next, the most valuable hypothesis to test next, which will be the one that's key to the result you're trying to get to. So it's going to be fascinating to see where this will go. But I'm hoping for myself that I'll have a prototype within a year.
And as you're hoping for the future, what is your intended outcome? What are you hoping for with this accelerated ability to do
Well,
science?
so Matt, one beautiful thing about this is how scalable it is. The instant the gateway is up and the database is populated with the ontologies that already exist out there. Many of them are already public, but they're in the wrong formats. There are a lot of ways to get the information into the knowledge assembly already. That's going to be very quick. And then once you have the gateway, instantaneously people can use it and participate collaboratively in accelerating science. So I believe within a year or two, all of those directions of science using this capability will be sped up 20-fold. So imagine a disease that right now pharma and biotech will take 20 years to solve. You get your solution in a year. And we're talking about 10,000 diseases, human diseases on biomedical side, and we've only solved 9,500. I mean, we've not solved 9,500. We've only cured 500 out of 10,000 diseases. So we need to speed things up. It's just crazy that we've got all this money pouring into pharma and biotech, and they're not getting the job done. And part of the problem is they're not motivated to. There's no benefit to pharma and biotech if someone's cured.
I was also going to say it opens up a second and related issue, which is from the perspective of climate change. If we are able to solve those
Yeah,
thousands of diseases and the population then that would, where there would be, let's just call it an attrition rate, is
fair
now,
enough. Yes, you get a population pressure potentially if you that's the whole longevity issue. So that's the whole branch of science. How are we going to deal with that? We're going to have some AI issues before that, because AI is already at the level of human intelligence. If you get into the AI field and you get familiar with the experts, they're quite concerned that humans are already behind the potential of the AI systems. And there's something called the singularity, which is when AI becomes 1,000 times smarter than humans. And I think that's within the next 3 to 4 years. Many people will say, I think because they're trying to avoid governments flooding in to regulate them, they say, man, maybe 10 years out, maybe 20 years out. You have some argument philosophically that maybe it will never match our consciousness, but it doesn't matter. It doesn't have to be conscious like us to be 1,000 times smarter than we are. So that's going to be an amazing challenge that we're going to have to deal with kind of long before longevity becomes a pressing issue.
understood.
But on the
Hearing that
climate
from
change
you,
problem, I agree.
right?
We need to speed our science up. We need to be, at least 10 times faster. And it's unfortunately, well, we're not going to stop climate change. We have Bill McKibben and Greta Thunberg and a whole bunch of activists out there saying we've got to stop at 450.org or 350.org. We've got to stop the increase in temperature. We can't go beyond 1.5 degrees Celsius. Well, we just passed 1.5 degrees Celsius. I'm afraid we're going to 5. We're going to a point where there's a lot of concern about the health of global ecology surviving. Will the fisheries survive? Will species survive? And if it's really bad for plants and animals, that puts a dangerous pressure on humans. The direct impacts on humans, I think we can survive. That's a wealth problem. That's adjusting and adapting. But the problem is we don't have the control over the corporations that are burning fossil fuels that we believe we do. And we don't even have enough leverage in our governments to control those corporations. And their interest, like pharma, is not human quality of life. They will do fine in a very, very hot world. Government survives. Corporations survive. They don't feel the heat.
So what,
The flood
from
kills
your
people.
perspective, what do we do if you were going to give us the top 1 or 2 things that we should do as a human species? What is that?
Well, certainly we want to develop renewable fuel. We want to do all of the things that we say we should do to stop burning fossil fuels, even though it's not going to be effective fast enough to stop global warming. But we want to do that because those fossil fuels are so incredibly valuable to us. I mean, those fuels are precious. That's a finite resource that's been stored over billions of years. And here we are burning it all up in 200 years to build what? Marshmallows, plastic toy guns. I mean, we're just building crap with this precious resource. So I say save the oil, use it for really valuable things, and move ourselves to renewables if we can. That means we've got to really go for efficiency. We've got to really pull back on our energy use. I suppose, I mean, good advice is we shouldn't travel. We should stay at home. We shouldn't be spending tons of money sending apples to New Zealand for storage and then the same batch of apples to Japan to get sprayed and colored and then brought back to the US for commercial market. It makes no sense to be moving all of this product all around the earth just burning energy. It has made transportation industry very, very wealthy. And that ties into Carlyle Group, very, very, very powerful international corporation that makes a lot of money by moving stuff around the world. And so, I'm afraid part of this new world order, which is use every corner of the world for economic productivity, comes at a huge energy cost. And it adds to the burden and the impact that we have to deal with.
Thank you. Where can people learn more about you and the work that you're doing?
Probably the best is LinkedIn. It's very, very complete, and you can get me there and you can contact me there.
Fabulous. I will make sure that the link is included in the liner notes of the episode. What a fascinating story you have through people that we've heard of forever, and you've got critical, pivotal roles with each of them over the course of decades. Thank you for taking the time to speak with me today and illuminate me and the audience on the important work that you're doing.
Well, Cheryl, thank you so much for letting me chat on these topics that obviously just they excite me and concern me deeply.
As they should, all of us. Thank you.
Thank you very much.
I hope my conversation with Dr. Justin Lancaster gets you thinking about the urgency of climate action, the power of AI in research, and the incredible potential we have to accelerate positive change at this moment in human history. Dr. Lancaster is proof that innovation happens at the intersection of disciplines, and that we all have a role in pushing science, technology, and humanity forward. Today, we learned that each of us can truly be a part of the solution of all that ails us. And until next time, keep using your voice, your passion, and your purpose to create the change that you want to experience in this world. I'll see you next time. If you enjoyed this, please like, subscribe, and share this episode with everyone that you feel it would benefit. Thank you in advance. And when you're ready to share your story and your work with the world, I can help. Visit CherylHunter.com to learn how. I am Cheryl Hunter, and until next time, know that your message has the power to change the world.